Okay. Starting circuits. Okay. Talk about Ohm's law. So by the end of this lesson, you will know how to describe voltage, resistance, and current, and describe how they're related to each other using Ohm's law. Okay. So we just went through this activity, making the light bulb turn on. All right, so there's this distinction between the side casing and the tip. So we need to make the current go around. Simply just connecting this like this is not a complete path. It's not a complete loop. It needs to start and stop at the battery. But doing this will make it light on because the electricity goes through the filament, lights it up. Okay. Now, the light bulbs you used were actually old school light bulbs. These are known as incandescent light bulbs. The next level or next generation light bulbs were fluorescent light bulbs. Those are like the long skinny tubes. They also have the spiral light bulbs. But the up and coming are LEDs, light emitting diodes. We might work with them a little bit, but just give you an idea of the evolution of light bulbs. Okay. All right. So electric potential difference, aka voltage. So this is the difference in electric potential from one spot to the next in a circuit. It's the difference in crowdedness from one spot to the next. So this is the role of this is it determines how motivated the electrons are to flow. A big difference between what we talked about last chapter with static electricity and circuits is this. Static electricity, when electrons transfer, it's in spurts, bolts, like pow, pow, like it doesn't, it's not continual. With circuits, it's a continual steady flow. Okay. Does that make sense? Like you never see a lightning bolt just like continually. It's okay. So with circuits, a common analogy they use is water flowing through pipes. It's a continual flow. In this idea of water flowing through pipes, voltage is likened to or compared to pressure, the pressure difference. Okay, so if you had a pipe filled with water, and on one side was 10 psi, 10 pounds per square inch, the other side was 10 psi as well, what would happen to the water in this pipe in between these 2 points? Nothing. They just sit there like, I'm under pressure, but that's all I know. But if you had 10 over here and 8 over here, 8 psi, what would happen to the water? It would go to the lower pressure. Does that make sense? If you had 10 over here and 3 over here, 10 and 3 psi over here, how would that be different than the 10 and 8? It'd move fat, like it'd be more motivated to flow because there's a greater difference in pressure from this point to this point. Okay, so voltage is pressure difference. It's the thing that makes it motivates the electrons to flow. Good with that? All right. So remember in chemistry how they taught you first that electrons orbit the nucleus like the moon orbits the Earth. Remember that? Like, hey, you got the 1s, 2s, goes around. Okay. And then later on, they're like, just kidding. It's like an electron cloud. It could be anywhere in this shape. It's going all over the place. Okay. What I'm going to teach you first is kind of like the moon going around the Earth model of how batteries work. Okay. This isn't actually how they work. It's a way to kind of get an idea. Okay. So this battery has this impenetrable wall between the positive side and the negative side. And the negative side, there are a bunch of electrons crammed together. Positive side, not so much. So if you were an electron, where would you rather be? The positive side or the negative side? Positive. So do you see the motivation? Okay. But they can't get through this impenetrable wall. Like, but there is an electric potential difference across this battery. So if you gave them away to there, you give them a complete circuit, a complete path from the negative to the positive, do you think they'd take it? Yep. And that's what causes bing, the light bulb to come on. Good with that? Tell your neighbor. Correct answer is C. Okay. B is not right because these electrons are like, well, I'm over here. I'd rather be over here. And this is like the electrons are being eaten by the light bulb. Not happening. Good with that? Okay. Now, in reality, here's what goes on. I don't know if you learned about electrochemistry, chemistry class, like voltaic cells. Yeah, all right. So there's a chemical reaction that takes place inside batteries. Okay, produces extra electrons. One of those chemicals likes electrons. The other one is okay letting them go. Okay, how big of a desire for those electrons determines the electric potential difference between the positive and negative ends of the battery. Okay. So that's what happens in reality. Like if you want to know more details, take a chemistry class next year, like a higher level chemistry class next year. So AAA battery. Anybody remember or know the voltage? Well, first off, what's the voltage on the outlet? 110, 120, depending on who you talk to. Okay. Does anybody know the voltage of a AAA battery? 1.5 volts. Okay. Compared to 120. That's why it's okay to hold them. Okay. Go to that. 120, 1.5. Does anybody know the voltage across a AA battery? 1.5. Wasn't that the same thing as the? Yep. Okay. Double A, triple A, both have 1.5. What about a C battery? 1.5 volts. What about a D cell? 1.5 volts. What about a 9 volt? 9 volts. Okay. So what's the point? Like, why do we have different sized batteries if they're all 1.5 volts? One is just the life of the battery. Like the D cell lasts a lot longer because there's more chemical reaction, like more chemicals in there to react longer. Okay. Second thing is just, or there's also this idea of internal resistance, which just produces more electron, but don't worry about that. And then there's also this idea of size. Like you don't want to be lugging around a 1 point or like a D cell battery for like a remote control car or something like a drone they have to fly. It's like, and it's like just so there's like physical limitations size wise. Okay. Correct answer is B. Okay. So in chemistry, do you ever hear of a reversible chemical reaction? Most chemical reactions are not reversible. Okay, but some of them are. So, like example of a physical reaction is reversible. So, like melting ice, going from ice to water, you can make water into ice. It's reversible. That's easy. Okay, but if you do it through a chemical reaction, um, most of those are not reversible. Like you produce a product and all this stuff, but some of them, some are. And so there's a lot of research into battery science, like the chemistry of batteries. Everything that is rechargeable that you plug in at night to recharge has a rechargeable battery, like your cell phones, any type of like remote whatever, or like things that you plug into to charge them up have a rechargeable battery. Electric cars have rechargeable batteries. Okay, good with that. Ben, great question. Um, they the chemical reaction ends up taking place so that there is no electric potential difference between like the electrons are equally crowded on each side. So what you have to do is plug it up, and that the plug makes the negative side look more attractive than the positive side, and so the electrons come back over here to charge it up again. You okay with that? Okay. All right. So that's power supplies and voltages and all that stuff. So the next variable, the next measurement we're going to look at is current. Current, the variable for that, kind of wacky, is a capital I. And the equation for current is delta Q over delta T. This is the amount of charge going by a certain point. The amount of charge, delta Q, is the amount of charge going by a certain point. Okay, and then over time is like each second for a certain amount of time. A more digestible way to say a certain amount of charge is number of electrons going by a certain point. Okay. All right. So what current looks at is this. It measures how many electrons go this is a wire, sorry. This is a wire. How many electrons go by a certain point, this point every second. You right with that? Okay. That measures current. So the unit that makes up current, what do we measure Q in? Charge in coulombs. And we measure delta T in seconds. Coulombs per second is equal to an ampere. Okay. The symbol for that is a capital A. Often we shorten ampere to amps. I don't know if you ever heard that, like for a circuit or electricity, like how many amps are going through. This is different than the amp that you plug your electric guitar into. Your electric guitar amp is short for amplifier, which has nothing to do with ampere, okay? But they both use amps. Okay. Go to that. Let's do this. So my new room, the light switches, they're not like on off, they're like dim, getting up there. So man, such a kick. All right. Sorry, this is. All right. So, correct answer for this one is B. Only B. So, let's pretend. So, it counts how many electrons are going by this point every second. It does not depend on the speed. Is it possible? Oh, sorry. Let's do this. If you were employed by the Department of Transportation to measure the current flow of I-65, one way to measure that would be to stand on an overpass looking over I-65 and count how many cars go underneath your overpass every second. 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 1, 1, 2, 4. Okay. Is it possible for fast moving cars to have the same current as slow moving cars? Tell your neighbor how that might be true. How could fast moving cars and slow moving cars have the same current? Okay, ready? Slow moving cars. 1, 2, 3. Pack like bumper to bumper versus fast cars. 1, 2, 3. Spread it out, but moving fast have the same current as the other one going bumper. Slow one's going bumper to bumper. Does that make sense? Okay, so it's not a measure of speed. It is a measure of how many go by a certain point every second. This is how we actually measure current on a river. It's not how fast the water molecules are moving. It's a measure of how much water goes by a certain point every second. We measure that in CFS, cubic feet per second. So if you've ever done whitewater rafting, you're going to check the current flow, how many cubic feet per second are going by a certain point every second. It's not the speed, it's the amount. Okay? So, I don't even know if this works. On your marks, get set, go! Oh, that's such a lame result. Marks, set, go! Ding. Okay. I did. It's all the way up. Okay, so the reality is, well, I'll tell you this analogy before I tell you the answer. If you, in the springtime, hook up your hose to a spigot, turn on the water, does water come out instantaneously? It takes a while. It's like, it's usually brown at the beginning, like, ugh. You wait a while, okay? Then, let's say you turn off the hose Put your thumb over the spigot so no water escapes. And then you turn on the spigot, you take your thumb off the end of the hose, how fast you get water coming out. Like instantaneously, like, whoa! The water's moving like the speed of light. It's like instantaneous. No, it just like bumped out the next guy. Like it just, does that make sense? Like it just, everybody just shifted. You're okay with that? So get this. When you go to a hardware store and you buy wire, it like comes pre-filled with electrons. Kind of like buying a hose pre-filled with water. They should like advertise that. I don't know what the marketing companies of there like they're missing like a huge like, hey, electrons included, like buy them here. Like, oh man, that's a good thing I get. I don't know where I'd get electrons if I could. Oh, I'm gonna get those. Like, there's not really wires without electrons, but you know, marketing, it's all how you market it. So when you turn on the light switch, the electrons are just being bumped out, just like the water molecules being bumped out in a hose. Does that make sense? Okay. So how fast are they going? Well, the plight of an electron, it's a rough life. So they're going through this crystal lattice of protons that it's just it's a rough thing. And so as the electrons go through, the path that they do is pretty violent. It's like it's a rough life. Okay. But they progress this way eventually. Okay. How fast they go this way, this is known as electron drift. You don't have to memorize this. I'm just giving you some context. But that's roughly around 3 millimeters per second. Pretty slow. It's like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. It's not very fast. Good with that? Okay. All right. Kids, this is a frustration of mine. If there is one thing in physics that I could change, it would be this. Okay. So electrons don't like to be down here, right? They want to be up here. So if we make a complete circuit, electrons go out of the negative through the light bulb and go into the positive. Okay? So the direction of electron flow is out of negative into positive. However, if you ask any electrician what's the direction of current, they will all tell you out of positive into negative. All of them. Not one will tell you different. They will say direction of current goes out of positive into negative. But there's nothing actually that moves in the direction of current. So why do we say that it does go out of positive into negative? Well, here's kind of the history of science here. So Benjamin Franklin, he was the guy that came up with this hypothesis that said, you know, I bet you there's charged particles super small, you can't see them, but one's positive, one's negative, and uh, one of those flows. I'm an optimist. Why not say the positives flow? So we started testing this hypothesis. This hypothesis had a lot of good stuff, and to the point where like, yeah, this Ben got it right, man. He's like, he's good. Like, this is great. Like, and so positive things are flowing. Then later on in history, we like discovered protons and electrons, and they did have a charge. And so a lot of this stuff what Benjamin Franklin thought was right, except for the fact that electrons were negatively charged, and they were the thing that flowed. And so we had this conundrum that we had all this science for like 100 years saying that positive things flowed out of positive into negative. And so the response to that was, you know what? It's worked for 100 years. It's just a sign convention. Let's just leave it. And like, blah, blah, blah. So like all science teachers are like, what? No, no, no. But it was like, look, we got textbooks, we got all these like all these manuals and all these how things are like, it's fine, it works. Like, why fix it if it's not broke? They're like, but it is. But no, it works fine. They're like, ah. And so at one point I was like, you know what? We're gonna overthrow this stupid thing. We're gonna start with the grassroots. I'm gonna start teaching students. We're gonna change the next generation. So I taught them like, hey, it's just electrons going out of negative into positive, and that's the direction of current. And like they'd come back like, Smiley, why did you teach us wrong? Like my professors like raked me over the coals. Like I failed this test because you told me. I'm like, ah. So here's where I'm landing. Recognize that there's nothing flowing in the direction of current. But if I ask what is the direction of current, you're going to tell me out of positive into negative. If I ask you what is the direction of electron flow, you're going to tell me out of negative into positive. Okay, that's just the world we live in. Sorry. Okay, good with that. Current goes out of positive into negative. Electron flow goes out of negative into positive. Okay, give that one a shot. Correct answer is B, out of positive into negative. All right, the last measurement that we're going to look at today is resistance. The variable for resistance is a capital R. It's like the first one is like, oh yeah, that makes sense. The unit for resistance is an ohm, and you're going to enjoy this abbreviation. This is capital Omega, like a horseshoe. Might take a little bit of practice to make. That is the unit for resistance, is ohm. Now, resistance has to do with conductor versus insulator. You were taught in like elementary school that something's either a conductor or it's an insulator. The reality is it's a spectrum. It's not just one box or the next. Okay, so things that have high resistance are good insulators. So like ceramics is a better insulator than rubber. Rubber is a better insulator than plastic. Plastic's a better insulator than wood. Wood's a better insulator than salt water. Salt water is a better insulator than steel. Steel is a better insulator than copper. Copper is a better insulator than gold. Okay, but gold is a better conductor than copper. Copper is a better conductor than steel. Steel is a better conductor than salt water. Salt water is a better conductor than wood. Wood's a better conductor than plastic. Plastic's a better conductor than rubber. Rubber's a better conductor than ceramics. Okay, so it's not a one box, X box. It's a spectrum. Okay. All right. Schematic diagrams. These are just symbolic ways to draw out a circuit. If you've ever seen a circuit diagram, a circuitry diagram, these are schematic diagrams. Okay. The symbol for a battery is a long stick and a short stick, drawn parallel to each other. The long side is the positive side. The way I remember that is positive sign has two sticks. So it's long side, negative side only has one. So it's shorter. Good with that? A resistor looks like kinks in a hose. So if we were to draw the schematic diagram of this circuit here, start with a battery. So this positive, negative, positive, negative. To draw wires, it's just usually lines drawn at right angles. So this is a wire, wire, wire. Light bulb is our resistor. Wire, wire, wire. This would be that. Schematic diagram of that circuit. Okay. Good with that. Okay. Last slide. Ohm's law. Ohm's law is just as important as Newton's second law was first semester. So like force is equal to mass times acceleration, F equals ma. Ohm's law says voltage is equal to current times resistance. Voltage is equal to current times resistance. So this is how you can write it mathematically. That's definitely the easiest way mathematically to write it. But conceptually, if we divide by resistance, we can explain things a lot better. So voltage, this motivates electron flow, or motivates electrons to flow. Let's do that. That's the pressure. Like, come on, let's move. Let's go, 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 go. Okay? That's voltage. It's the pressure. Resistance resists electrons flowing. So resistance resists electrons from flowing. You see the conflict of interest here. And one's like, come on. The other one's like, whoa. So there's this battle going on between voltage and resistance. Current, this is the flow of electrons. This is the result of the battle. Okay, good with that. So what could I do to voltage to make current increase? Increase the voltage. Everybody see that? What could I do to the resistance to increase the current? Could decrease the resistance. Good there. Okay, got a worksheet due tomorrow. Pretty basic.